All right, we're going to be extending our talk about infectious disease modeling, and I'm going to talk about deterministic compartmental models now, which is the most common type of modeling that you see in epidemiology. Basic ideas and assumptions. There's some sort of basic, any model is going to have assumptions, be it sort of transmission modeling or regression modeling or any other kind. In compartmental models, one of the basic assumptions is that the populations under study are divided into distinct compartments, so they travel through different states of disease. We're going to talk about what those mean in a minute, but the idea is that people can only occupy one state at a time. So you're either healthy or you're sick, for example. Rates of transfer between compartments are expressed mathematically as derivatives with respect to time to the sizes of the compartments, and these are generally systems of ordinary differential equations. Don't be alarmed by this. We're not going to go into any sort of heavy math with this at this point. But the point is that people flow through these different compartments with a specific probability. And the number of people that flow through these compartments at any particular time is related to the number of people within all the other compartments. So, for example, more infected people will result in more people becoming sick because there's more chances for people to be exposed. One assumption is the community size is constant over the duration of the epidemic and is a large number n. The simplest case, the infection is transmitted primarily by person-to-person contact, for example, measles, but not all compartmental models are strictly person-to-person. There's complex models out there that model, for example, vector-borne disease, which is one thing that Ross and McDonald did. Individuals mix uniformly. These are basic assumptions. You can get more complex with model and relax these assumptions a bit. But the idea here is that every individual has the same probability of encountering any other individual as any other individual. So, when we're looking in class, for example, all of us have the same probability of encountering one another and thus possibly transmitting disease. The simplest compartmental model is this, the susceptible infectious model. We have two compartments in this. One is susceptible, people who have not become exposed to the pathogen yet, and one is infected, people who have. People move from the susceptible state to the infected state upon being exposed to the pathogen. B, or beta, is the probability that a person moves from the susceptible state to the infected state. So basically, at any time step, this is the fraction of people who become infected. So you have time t. Say 5% of the people will become infected. 5% of susceptibles move to infected. And the number of infected grows at that point, as you can see in the figure to the right. One line is susceptibles and one line is infectious, and you can see as the number of susceptibles goes down over time, the number of infected goes down because people are moving into one state. In differential equations land, this is what the equation would look like. Population n is the sum total of the population of susceptibles and infecteds. So people can only be in one state at a time. We can get more complicated with this. People can die, for example, when they become infected. So the population at that point is not necessarily constant. People are moving out. But we can also include births, so people can come in. And this is just to show you that you can get a little more complicated with these models. We can have a fixed population n, but we can also have a population that has people leaving and coming in, a dynamic population. And we can also have situations where people just remain infected and don't expose the susceptibles. It's kind of a strange plot. A little confused by this, but we'll move on with this. These models get more complicated. So this is the most famous. People will talk about SIR models. So people move from being susceptible to becoming infected. They're infected for a period of time, and then they recover. So people can occupy one of three states in this case, rather than two. Only infecteds are able to transmit to susceptibles, and so as the number of susceptibles go down, infecteds goes up, and then people recover. And then over time, you might see something like the epidemic burnout. So here's an example of what an SIR model would look like over time. The blue is susceptible, red is infected, and the other color is recovered. I'm colorblind, so it's kind of difficult for me. We have time on the x-axis. Time goes forward, number of susceptibles goes down. The number of infected at any time goes up and then down as people become recovered, and then eventually everyone in the population recovers. There are the differential equations that go with this. Now, in this case, we don't have births and deaths, so S plus I plus R equals the total population. People can only occupy one of those three states at any time. What I want you to notice about these equations is there's these different parameters. So we have parameter beta, which is the parameter that is the probability of a susceptible becoming infected at any point in time. The gamma parameter is the time, the percentage of infecteds that recover at any time. We can get even more complicated with this: susceptible, exposed, infected, recovered, where there's an exposed state where people are exposed to the pathogen, but maybe not necessarily infective yet, or maybe they're just asymptomatic yet. And so it depends on how you view this. We can get even more complicated with this, having multiple populations interacting with each other. So, for example, the exposed or the yet infective are able to infect other susceptibles in one of the other populations. We can easily draw arrows from the I category over to S as well. These types of models are good when you want to sort of like, for example, look at different age groups within a population, or different social groups, or different geographic groups, or whatever, or even between vectors and hosts. There's all different kinds of things you can do with these types of models, and it can get really complex really quickly. So these are some different types of models: SI, SIS, susceptible, infected, susceptible. So people move back into the susceptible state and then are able to be infected again. SIR and SIRS, so people can be recovered and immune, or they can become, susceptible again. SEIR and SEIRS. So when in doubt, just add another compartment, just add another population. You can do whatever you need to do. So that's a little overview of what SIR models are, compartmental models are. I don't expect you to know the complexities of the differential equations. I just want you to conceptually understand what these are and how we would approach them. And so next we're going to be talking a little bit about applications of these models. Stick around. If you have questions, reach out, because I am here to help you.